Welcome to longitudinal and transverse waves. So we've previously looked at waves on a string, sound waves and light waves. There are two main types of wave. There are transverse and there are longitudinal. The trans in transverse means across, and for waves on a string and for light, they are both transverse. And this is because the direction of travel of the wave is one way and the oscillation that's creating the wave is at 90 degrees to it. Hence, across or transverse. So we've got waves on a string is an example of transverse waves. Light, and if we're looking at earthquake waves as well, then we are looking at shear waves or S waves. Examples of longitudinal waves, which have oscillations along the direction of travel. So in this example, we have the wave moving from left to right, and in that direction, we have the oscillation going backwards and forwards in that same direction. It is parallel. The oscillation is along the direction of travel of the energy of the wave. And examples of longitudinal waves are sound waves and another type of earthquake wave, which is a pressure wave, which is essentially a sound wave, known at GCSE level as P waves. It's important to note that light is a transverse wave, and it actually has two parts to it. So it has the transverse electric component and it has the magnetic transverse component as well, which is at 90 degrees to it. So transverse waves can actually be oriented in different directions. So remember that a light wave is also known as an electromagnetic wave. You will have studied the electromagnetic spectrum. And so what we have is we have the electric component and we have the magnetic component, and they're actually at 90 degrees to each other. But this is still a transverse wave. So the oscillation creating the electric component would be up and down, and the oscillation creating the magnetic component would be at 90 degrees to it, but it's still at the 90 degrees to the direction of travel. This is a simulation of polarization. So polarization is something that affects transverse waves only. We can see in the top left corner that we have unpolarized light approaching the simulation. And what that is it's a collection of transverse waves oriented in different directions. We've got some waves that are coming in vertically oriented, some that are coming in horizontally, and others at strange angles. They're all moving from the left side towards the right, and the oscillations are all at 90 degrees to the direction of travel. But in that last direction, whether they can be vertical or horizontal or in between, they are essentially randomly oriented. As they get to the first filter, you'll notice that this filter has a vertical orientation. You'll see that only the vertical oriented transverse waves are allowed through. You can't do this with longitudinal waves. This only works for transverse. So we can see that this filter cuts out all of the light except for the vertically polarized. I have another filter down here in the bottom right corner, and I can change its orientation. If I rotate it, then you can see that that vertically polarized light, those vertically polarized waves, are blocked by this filter because it's now not oriented in a direction to allow them to go through. So we've seen that polarization is something that can happen to transverse waves and transverse waves only. So if a wave is capable of being polarized, we know that it's not going to be a longitudinal wave, it has to be a transverse wave. Light is a transverse wave and light can be polarized. We use polarization and these filters in things like sunglasses, because what can happen is that light coming from the sun reflecting off surfaces towards our eyes is unpolarized. And sunglasses, which filter out all light except for that in the direction of the filter, reduces the amount of light entering our eyes. Sunglasses tend to be vertically polarized, and when you get light reflecting off smooth surfaces like water or snow, it tends to be horizontally polarized. So this vertical filter reduces a lot of the glare that we get from those sort of sources. Another important use of polarization is in transmission and reception aerials. So if you have a transmitter and it is giving out television signals, and you have a television aerial, you need to make sure that your television aerial is aligned the right way to receive the signals. So the way that the aerial works is the receiver has electrons in the metal poles, and those electrons are ready to be oscillated up and down along the length of this aerial. If it's aligned horizontally, then they're going to be oscillated horizontally. So if you have your aerial set up like this, ready to receive a vertically polarized transmission, then you need to be pointing it at a vertically polarized transmitter. Sometimes you'll find different areas, they will replace transmitters with newer ones, but maybe the polarization changes and it becomes a horizontally polarized signal, in which case you need to change your aerial. It needs to be realigned so it's pointing at the new transmitter, and then you need to set it up so that it is aligned horizontally, ready for those electrons to be oscillated in the same direction as the signal.